Hello, welcome to video 2 in our lecture Advanced Mathematic Modeling. And I want to start this lecture with the question, what are stochastic effects? What we are dealing with in this lecture. And as usual with these fundamental notions, it's very hard to get a definition or get a grasp what we are really dealing with. But I want to at least to give some motivation. And let me make this a bit bigger so we have more space. So for people who have studied their normal modeling courses here in Oldenburg in the bachelor with me, we're dealing with differential equations, with deterministic models. So typically we have a state variable x and it depends on time. And then we have some differential equation and we say x dot, the time derivative depends on x. We have some model. And then we can solve the model from initial position and then we get some kind of trajectory when we have a deterministic model. So starting from the initial position, the whole future is already defined. The whole trajectory of our state variable is defined. We have only a single trajectory. And so that's basically the whole frame of all modeling with ODEs, with differential equations. So, but what's the reality? Let's assume you would make an experiment. Let's say assume X is a population number or concentration of a chemical reaction. And so we make an experiment again as a function of time. We want to know what's our state variable. We start, maybe we can prepare our experiment that we can start at a precise defined state at the time 0, and then we run the experiment. Then maybe let me put in here the solution to our model. Maybe this was the model here on the left side, and we run the experiment, and then maybe we see something like this, that the outcome of the experiment maybe resembles the model, but we see some deviations. And so we say, okay, there's some stochasticity. So we have the deterministic solution if we have a good model, and the reality is a little bit deviating from this. And maybe I should try here. It's now the experiment. And in our modeling lectures, we were able to cope with something like this, that we put in some random numbers on the right side of the equations and then kind of can simulate some twiggling around this solution. Interesting is now when we repeat our experiment. Let's say we run the experiment again, then we will not repeat exactly this random trajectory here, so this twiggling trajectory, but we will get typically something else. Maybe now it looks like this. Let's repeat the experiment again, and maybe we get something like this, and another one we get something like this. Yeah. And so the important property when we then realize repetitions of our experiment, when we have many realizations, and we have very different outcomes. And so we say the outcome of our experiment is a stochastic process, but we see also that all the outcomes of the experiment kind of mimic or scatter around this deterministic solution. So there is a general tendency very often in such data, but we see some scattering around. Yeah. And then the question is, how can we take these effects serious and start to make models which really implement this randomness? And then the question is, where does this randomness come from? What does it mean that we cannot repeat this experiment? Yeah. Of course, this scatter depends what you're doing. When you have a physical experiment, you can be maybe very close to such a trajectory. If you're in ecology or life science, you will often have very large deviations. But then there is also things, there can also be surprises. Let's do another repetition of the experiment. We go until here, we have a large deviation, and suddenly, by chance, our state variable hits the 0. And let's just say 0, and if it's a population number, this is an absorbing state. Once the population is gone, it can never recover. And then we have a solution which stays 0. Okay. And suddenly we have a surprise. We can have an outcome in our experiment that our population goes extinct and is not there, which is very different from the scattering around this general tendency. Yeah. So including stochasticity, or taking it serious, can suddenly have lead to very different properties than just scatter around the deterministic trajectory. Otherwise, we could maybe stick to this here and just say maybe we have here some margin of error, and then say, okay, we are happy with this, so we just make a deterministic model and then say, okay, maybe the reality will just scatter a little bit about this. But as you see, in the stochastic, if you take all the stochastic events into account, this might give very different outcomes. And so the question is, how can we introduce such things into a model? And maybe a more modest question would be, how can we describe and characterize the scatter around this? Is the scattering around this mean here? Is this symmetric? Is this broad? Is this narrow? Can we characterize this? And even there can be surprises. For example, when you have these extinction events, such a distribution around would not necessarily be unimodal, so you could have here different modes and so on and so forth. So that's kind of the one motivation why we would like to have models which are basically inherently embrace this stochasticity that can be in such outcomes. And if we have such models, then the question is, how would these models relate to such ODE models which just can describe a single trajectory? Maybe more subtle questions are, where does this scatter or the stochasticity come from? Where is the origin of this? And when you think about this, you find this very often. Yeah? So such stochastic processes are everywhere. And take an example. I mean, one of these paradigmatic examples that are always used is we throw a dice. So we take an example. We throw a dice. So we a coin. Sorry, we take a coin. Throw a coin. More simple. So we have here a coin, which can have head or tail, and then we throw this. Here we have the floor, and then this coin is doing some weird, complicated trajectory, and then it lands on the floor, and there's only two possible outcomes. Either we have head, which we usually call H, or tail, T. That's the only outcomes of this experiment. And now in principle you could say, I could set up a deterministic model, which not only has only a single state variable, but more. It's a higher dimensional model. But now forgetting in the moment about quantum mechanics and so on, in principle this is a deterministic process. And if I can, if I know the initial position, orientation and velocity of my coin, in principle I could calculate what is the outcome. So, but then how possibly can I call this a stochastic process? Because it's deterministic, forgetting about quantum mechanics or something like this in the moment. And so you see the question, what is deterministic or stochastic, is not easy. It's rather philosophical question. But let us assume this would be a deterministic process. Why should I still treat this as a stochastic process? And the thing is, so let's assume what are the initial conditions of what are how many variables we need to characterize the initial position of the coin here. So the initial conditions. So we need the mean, the position of the center of gravity. So this has three dimensions. So we need three numbers for the position. Then we need the orientation. This is again three numbers. Then we need the velocity of this coin, and maybe we need even the rotation of this, like in which direction is this rotating. So then we have maybe something like something from the R12, a 12-dimensional state space. We need 12 numbers to determine the position, velocity, orientation, and rotation of our object. And then we run the experiment. And so from this high-dimensional space, this 12-dimensional space, we go to a very simple set of outcomes, because we can either have head or tail, so we go to a binary outcome. So we have a tremendous reduction in the dimensionality of our initial conditions to the outcome of the experiment. But in principle, if we know the initial condition here, we can, with our model, calculate the outcome. So, and now there could be different possibilities. Let's make here a sketch of our 12-dimensional space. So that's our space of initial conditions. And now for every point here, we give a color the outcome. So if I make a black dot, this means I have head. If it's a white dot, it's tail. And now it could be like this, that we have here such an area that all initial conditions in this environment here all lead to the result head, and all initial conditions outside of this would lead to tail. If this would be the case, then we could say this is a deterministic process, the throw of the coin. Because, I mean, in principle, I will always have some uncertainty about my initial position, but the uncertainty doesn't matter, because if in a small environment around one point I have always the same outcome, so I can be quite certain if I in the black cloud here, initial positions in this black cloud, so the coin is somewhere positioned in space, we always get head, and if it's positioned somewhere else, it will be tail. So this would be a trivial example, and this would be, or we could treat this as a kind of deterministic process, and only for initial conditions which are on the boundary between the black and the white area we have some problem, we don't know the outcome. But the example of the throw of a coin, such a picture would be rather different. Yeah? So if we would do this, we would get here a random pattern. Yeah? So for some initial conditions, we would find the outcome head, but for infinitesimal deviation from this initial conditions, we find the outcome tail here. But since in reality we always will have some uncertainty about our initial conditions, we will always have a small environment, and we will say, okay, the coin can only prepare it so and so precisely, so we will have some small environment. Yeah. But in this environment we still have a lot of different outcomes, because we have here this random picture, or this scattered picture of outcomes. This means for this initial conditions in this environment, so I write this down, initial conditions in such a circle, we don't know what the results will be. We have uncertainty of the outcome. So this means even if in principle the process and the trajectory of the coin is a deterministic process, if the mapping from initial conditions to the final result of our experiment is something like this, which basically means probably this is a chaotic dynamics, then we can only treat this experiment as a random process, because we have no way to determine before the experiment what will be the outcome. So we need to deal this as a stochastic process. The only way what we can do is done. Treat this as a stochastic process. Yeah? That means we can only give a probability, what's the chance that we have a head or tail, but before we do the experiment we have no way to determine the outcome. And you see the similarity to this what I described here above. And here I said we cannot repeat the experiment, every repetition will lead to a different outcome. Exactly the same we have here. When we repeat the experiment we will prepare our coin a little bit different than before, but then the outcome is not determined, so when we repeat the experiment we will always have a different outcome. And so what we have here shown or discussed there in this hypothetical or in this simple example of a coin, you will find in many different systems. In the theory we will very often have coins, dice, roulettes and so on, but card games. But in reality, if you have your population numbers, weathers, stock markets and so on, you have same process also. So we have, so what's behind now that that we have to describe a certain process as stochastic? It's that we really believe that we are not able to predict the outcome of an experiment or the future of our state variable. Even so, we are not able to do this, even though maybe in principle it would be even determined, but we have no ability to do this. And then we need concepts of probability, likelihood, and so on and so forth. And what's also interesting is that this likelihood or this probability is only before the experiment. After the experiment, all this uncertainty is gone here. So we need a stochastic process only to describe the possible outcome of an experiment before the experiment has been done. So that was maybe some motivations or to show you the inherent difficulties or problems to define what is or understand what is behind stochastic effects, stochasticity. This goes a little bit into maybe even in science, philosophy. In the next video I will show you how we can deal with this likelihood of the outcome of such a stochastic process mathematically. Okay, thank you.